Hi, I'm NawaMan. I would like to show off my solution to the 1 billion row challenge. The 1 billion row challenge was proposed by Gundam Morling on January 1st, 2024. The challenge is to write a program that can read a CSV file with 1 billion rows of data. I saw the original Twitter post on that day, but I thought this was an IO bound problem, which I'm not interested in, so I didn't pay attention to it at all.
However, sometime in August, I saw these two YouTube videos which sparked my interest. I then learned that the benchmark would be run on a machine with a large memory, which changed the nature of the problem to be CPU bound. Despite thinking that the clever Mr. Moring may just want someone to solve the problem for him, I decided to give it a try anyway, 8 months late. The main work took about 1 to 2 weeks, but more time spent setting up benchmark on AWS and make these slides, which I need to learn Swell first to make them. I have many ideas for this slide, like animation and stuff, but it already take a month, so here's what you got. The result? Pretty good actually. The program ran in 1.8 seconds on one machine and 3 seconds on another. This is likely due to different disk speed. It's still I/O bound problem. You can click to see the details here. The code achieved this without using hard to maintain unsafe or hard to read bitwise strict, and it's not using ground VM either. And I think it's quite readable code. By that I mean it's well partitioned and use regular idiomatic Java. You can see the code on GitHub. The whole thing is less than 450 lines long. Before talking about the solution, let's review the challenge in more detail, which is to read a text file containing 1 billion rows of measurements. Each line contains the weather station name, or city name, we can call, and temperatures. Rows are delimited by the new line characters. Station name and the temperatures are separated by the semicolon. Station name is encoded in UTF-8, that's important, and is no longer than 100 bytes. The temperature will range from minus 99.9 to a plus 99.9. That is 1 to 2 digit before the decimal and 1 digit after the decimal always, with the optional negative sign. The aim is to calculate minimum, maximum, and the average temperature for each station, and then print the result in the Java sorted map to string format. The whole program have to fit in one file without any external dependency, and this is the machine it will be benchmarked against. Here is the high-level view of the solution. I will go over the details in the coming slides. Starting from the file, we read it into chunks. For each chunk, the data is then extracted and put into a map, a hash map to be specific for performance reason. The station name is used as the key of the entry, and the value of the entry is an object containing min, max, sum, and count. If there are more than one entry from the same stations, they will be combined. After that, two maps of different chunks will be combined into the larger map until there's only one map left. And then this map, which is still a hash map, is sorted. And after that, it gets printed out. Pretty straightforward. The first trick used to make this fast is to use virtual threads to read and process each chunk in parallel. Virtual threads are also used to concurrently combine statistic map. After some experiment, I end up splitting the file into 1024 chunks or 32 times of the CPU count. In the code, you can see that I create virtual threads executor, and then for number of chunk, which is 32 times the CPU count, I create is extractor and submit as a task. At the end of the task, the result will be added to the statistic queue right here. Then there's a code to pull the statistic out as a pair, and then absorb one into another. And every time we do that, we increase the chunk count in that statistic. And if the chunk count of the statistic found is the same with the chunk count, that means we're done. We shut the whole things down and sort the statistic and print it out. As mentioned earlier, I have an idea to make animation here, but no time. The next trick is due to the large size of the file. The read speed is a big factor of the overall performance for sure, but the result data structure from that read, it also contributes to the performance. From that pro and con, we can look into the alternative. The first alternative is to read the whole files into a string. But that means we need to store the whole files into a string, then break it off into another chunk, duplicate the memory, and then as a station name, we further duplicate the memory used. So this is not a good option. Similarly, with the lines, if we read it into the lines into a string, that means duplicate here and then also duplicate here, which is not a good thing. We can use random access files and read byte by byte, which is really fast. However, random access files use integer as an index. An integer is not much enough for these 13 gigabyte files, so this is not an option. The last two options involving using mapped file to memory. The first one will map the data from the file to native memory, which is outside of JVM, which is supposed to be very fast. Actually, it's very fast. And the second one, read the data directly from the disk to the memory, but inside a heap, which is slower from the first one. However, the first alternative here, direct memory, is slower to access. So overall, read to the heap memory is the fastest solution. It's the one that I go with. We touched a little bit in the previous trick that creating string is expensive because it needs to hold isolated array of bytes to store its characters. Let's review the journey of the station name, which is the things that will hold a string through the whole process. First, it gets read from the file into a chunk, and then it got recognized as a station name when we parse it and put as a key map. To put in as a key map, it needs to calculate hash and do equals and things like that. And then the similar things happen when we combine, because the combination is just getting the key from one map and look it up in another map, then perform the combine. After that, we use the key to sort the entry. This sort had to be done as in UTF-8, and then we print it out. If you consider this journey, you see that only the last two steps, that station name need to be a string because the sorting have to be in UTF-8, which is a string. So without wasting memory to things that we got thrown away, by that I mean when you read the word like Bangkok and put it as a key here, and then when we read another Bangkok entry, which found to be already there, this thing got thrown away, right? So without converting the data into a string and it get thrown away, we save some processing and improve the performance. To conclude, if we delay the conversion to string for the station name to the very last, we save both the processing time and the memory use. So if we don't use string, what do we use instead? Byte array, of course. The byte array is used to store the station name as we read from the chunk, which itself is a direct memory map, if you recall. And then during the process of reading, we also calculate the length and the hash at the same time because we're going to use the station name as a key map. It needs to have a fast echo check. Just a reminder, A hash map will use hash code to shortlist the number of possible key for the match, even with one matching hash code. If the key already exists in there, for example, this second Bangkok, when read from the chunk and look it up, the Bangkok key already exists in the map. That byte array that we used to store the second Bangkok can be reused because this is not going to be used. The one inside the map will be used. But if we read, let's say, this Da Nang here is not already in the map, then we will reuse the byte array for this. So we have to create a new buffer. Let's see in the code, might be clearer. So this is a station name object. When it is asked to read from the byte buffer, you just go through it byte by byte, right? And look for the semicolon. And this is what I mean, it calculates the length and the hash at the same time. The hash it used as is, but the byte array it used when we do equal. So hash map will check the hash code first. If they're equal, then it will call the equal check method. At the end of the day, we need to make sure that the bytes are equal. The one that in the map and the one that we just found, they have to be equal. So it have to go through this equal check. And we can do it using bytes, don't need to reconvert to string. When we need to compare during the sort, we need to compare it. We can convert this byte into string. This is where it used. The station name will read itself from the buffer. Then will be used as a key to get the statistic. And if there's no statistic around, one will be created. So if it created here, the station name will be used inside that statistic. So if it's a first of its kind, the station name from the statistic will be the same as the station name that we have here from the outside. In that case, we cannot reuse this station name. We have to create a new one. But otherwise, the station name, this guide, can be reused in the next loop. The next trick is to optimize the temperature value. The temperature value is supposed to be a floating point number, but floating point number is not precise, even for one-digit decimal. And converting string into float is quite expensive. So what we can do, we can save the temperature value into an integer, just times 10. For example, instead of 14.2, we use 142. And this is where the code is. Temperature buffer, when we read it from the buffer, pretty straightforward. The next trick is quite low level. It has to do with how hash map works. As mentioned earlier, the hash map will use hash code to find short lists of possible keys, but because key can collide, so at the end, it will have to do an equal check to the key to be sure, even with the short list of one key. So it is critical to make sure that the equal check of the key is really fast. And to do that, we will make use of the new vectorized API. The good news is it already built into the existing code. Let's see what I mean. I showed this earlier that the equal check of the station name object, which we use as the map key, basically do the array equal for its bytes. And I was saying that the vectorized API is built into this equal. So if you go into the equal of the array, you see that it used array support dot mismatch. And inside the array support.mismatch method, it used the vectorize check. The last trick helps improve the combination speed. We already discussed that echo check is a critical component to make get and put data into map fast. And then we do a lot of that, as you can see, when we extract the data out and combine them, right, in per chunk. But when we combine each map into the bigger map, we also need to do get and put the key, a lot of them, because there are 10,000, because there is 1,024 of these, so there are a lot of these combined. To help speed things up, I normalize the station name. By normalize, I mean for the same station name value, I'll give it a unique ID as an integer. So this way, when we need to compare, when we need to do the echo check to the station name, we can just compare the integer value of its ID. How that's done, start here. So when we detect that the station name, it's a first of its kind in the chunk, we then put the station name into the station name queue on this line 371, because we don't want to do for all the name, of course, only one per chunk. And then in the station names queue, so when we add it in, it will go to the queue, and then this will run in a separate threads by pulling out the station name and then try to see if it's already in the map. If it's not, we generate a next integer and return it. But if it's already there, we just return the integer, assign it into the ID fields of the station name. So when we compare, do the echo check to the station name, we see if the IDs of this object as well as the ID of the other objects has already been assigned. So the normalization has already been done. If so, we just compare the ID. So this skip over the expensive echo check to the byte. Turn out this speed things up quite a bit. To sum up, this is my solution for the 1 billion row challenge. It get quite a good result and is quite comprehensible as well. Here's some tricks I use. First, I use the virtual threads to parallelize the processing of data. I use memory map file to quickly read data to memory. I delay the conversion of station name to string until the very last step. I use by array to store the name string instead. I use integer to store the temperature's value rather than floating point number. I use vectorize API to do the name comparison, which is used a lot to look up and store data in a map. And then I normalize the station name into ID to speed up the lookup of the name in the map further. That is it. Thank you very much for watching. Uh, Again, I'm NawaMan. You can find out more about me here in this link, and you can get the whole of the code, take a look at the code in this link. Thank you again for watching. Bye bye.